Hello everyone, I hope you are doing well. This video is about to find the Miller indices of the planes, and in this video I will explain the method, the general method that you can use to find Miller indices of any kind of plane. And let's begin with the method. And first of all, I'll explain the general steps that we take while finding the Miller indices of the plane. So the first step is to look at the plane, okay, that is given to you for which you want to find the Miller indices, and you have to see whether this plane passes through origin or not. Okay, whenever you are given a plane for which you want to find the Miller indices, there is a predefined coordinate system whose origin is defined also. Now the plane should not pass through the origin, so if it is passing through the origin, then you have to change the coordinate system. So this is the first step in which we define the coordinate system, the appropriate coordinate system that we will use to find out the Miller indices, and that coordinate system should be such that the plane should not pass through the origin of that coordinate system. Later on we will see the examples and it will be more clear to us. Secondly, we have to find out the intercepts for the plane. Okay, now for the three-dimensional lattice system, there are the three intercepts that we need to find out, and this is x-intercept, y-intercept, and z-intercept. And actually, for finding the Miller indices of the planes, finding the intercept is the crucial part and the trickiest part. And if it is done, then you are good to go. Like everything is sorted. So this one will be the main challenging thing, and this is the most central important thing that determines what will be the Miller indices after that point. So when we have found the three intercepts, the third step is to take inverse of these intercepts. Okay, 1 over x, like 1 over y, and 1 over z. We will take inverse of these values, and after that we will make sure that none of the value is a fraction value. For example, after taking inverse, if we get 2 for this, 3 for this, and 1 over 2 for this is a fraction that occurred. So we have to remove that fraction by multiplying the three inverses with the LCM of the denominator. So we can take simply the LCM, which is actually 2 here, and we'll multiply it with all the values, and after that the number that we got will be the final values, and these will be the Miller indices, which will be enclosed in a round bracket, and this is the final representation for the Miller indices of plane. So following this procedure, we will get the Miller indices for the plane, and as I told earlier, this is the main part. And yeah, we'll find Miller indices for 6 to 7 different kinds of planes. So let us start with the first example, and the first example will be the simple one, and we'll move towards the difficult levels gradually. And please avoid the voices of animals in the background, as I live in a village, so this is a common thing here and I cannot control their voices in the background. So let us start. Here is the first example, and these are the problems from a book called Material Science for Scientists and Engineering, or something like that. I have mentioned its name in the comment section and also in the description box if you are interested in the book. So this is the first plane, and as you can see, the first step that we mentioned is to check out whether our plane passes through the origin or not. So this is the plane 1, and this is the plane that we are interested in to find its like Miller indices. So now here is the coordinate system, predefined coordinate system that is like predefined, and this is the plane, and we can see here that none of the point of the plane is passing through the origin. So this coordinate system qualifies for a method, and there is no problem in it. So we'll use that coordinate system by taking x-axis in this direction, y-axis as this, and z-axis as this. Okay, so first step is done. We have defined our coordinate system, and I am taking these lines as our coordinate system. And for just to show you properly, I am drawing it also on the paper. It's up to you if you want to draw it or not. Like if it is drawn on your question paper, then there is no need to draw it again. So it's totally optional, and it's up to you that whether you want to draw it or not. But to properly explain it to you, I am drawing it. And this is the origin they have predefined, and this is x-axis, this is the line for y-axis, and this is the line for z-axis. Now in case of the planes, the axis lines matters a lot. Okay, so you have to take care which are the axis lines. So this is the positive x-axis, positive y-axis, and this is the positive z-axis. And we can see here that one of the point is like there, okay, at the end of the unit cell here, and one of them is along the x-axis, and it is about at the center, and the last point is at the end of the unit cell along the y-axis. So this is like there. I'm just redrawing it. Okay, so this is the plane whose Miller indices we are going to find, and the first step is done. We have completely successfully defined our coordinate system. The second step is to find out the intercepts. Now intercepts are the point along the axis which are like intersected by the plane. Now these are the lines. This is the x-axis, this is the y-axis, and this is the z-axis. So we can see here that the plane, if you consider the x-axis alone, the plane is intersecting the x-axis. This is the axis line, and the plane is intersecting it at this point. Okay, so this point will be specifically called as x-intercept. And the point of the plane which is intersecting the y-axis, this is the line of y-axis, and it is intersecting here. The plane is intersecting here. This is a part of the plane. This is the whole plane, and it is intersecting the y-axis right there. So this point will be the y-intercept, and this point will be the z-intercept because it is intersecting the z-axis at this point. So in all questions, we have to find out where the plane is intersecting the axis. Okay, the three respective axes. Now these are intersecting at positive axis. This is lucky case, but there will be cases where the plane will be intersecting it in the negative directions of the axis. Like this is the positive x-axis, and the plane maybe is intersecting in the negative x direction. So the Miller indices will be negative in that case. So there will be also that kind of cases that we will see later on. So this is the simplest one, and we can see clearly here that the plane is intersecting at these points on the axis. So let us see what these points are. So first of all, the x-intercept, as you can see here, is 1/2, because the whole length, if the point is lying at the end of the unit cell, then the length parameter that will take will be 1. Okay, and if it is intersecting halfway the full length, then we'll take the half of it. We'll see what fraction of the total length is the point located, like where the point is located, what fraction of the point as compared to the total length. So this is halfway, and that is why I took half as its x-intercept. Now the dimensions of the unit cell doesn't matter here, okay, because we are taking fractions here. So if total length is 3 centimeter or anything like that, that doesn't matter. The only thing matters is the fraction, and it is half the full length. Okay, this is the full length, this is lying at the halfway, so that is why I took half as the x-intercept. And the next one is this one, y direction. Let us take it in that pattern, x, y, and z. So we can see here that the plane is intersecting the y-axis at this point, and this is the complete unit cell length, the complete one. It lies at the edge, so that is why we'll take y-intercept as 1. Okay, and in z direction we can see here it is also lying at the corner, so the z-intercept will also be 1. All right, now it was clear enough that it is lying at the halfway, because we can see here that the point here, if you draw its projection above also, it's halfway. Okay, it is lying at the halfway. That is why I took half. That was the best estimate that we can take about its position. So the best estimate will suffice. So this was the best estimate. Now we have found the three intercepts. Now the next step is to take the inverse, and let me write them in order here, and we'll take the inverse of all these, and the inverse of 1/2 is 2, the inverse of 1 is 1, and the inverse of 1 is again 1, and we will enclose these numbers in brackets, in round bracket. And first we'll write the inverse of x-intercept, then inverse of y-intercept, and then inverse of z-intercept. Okay, so yeah, and because there was no fraction right there, that is why we do not need to remove any kind of fraction, because there is none there. So this is the final Miller indices for this plane. Okay, now we'll find the Miller indices for the other plane that is also lying besides it, which is labeled as plane 2 here. And we can see here that the first step is to see whether the plane is passing through the origin, predefined origin or not, so that we have to redefine the origin or not, so to decide. So we can see here that this is the plane 2, and this is the coordinate system. Okay, and these are the lines of coordinate system, and here is the origin, and the plane is lying right there, and it is clearly not passing through the origin. That is why there is no problem at all, and we'll use that coordinate system again. And the plane is here, and we can see here that it is halfway along the y-axis from the origin. So let me draw it right there, and there is another plane side by side, and it is at this half point, half the distance from origin along the y-axis, you can see here. Okay, so this is the plane 2. Okay, and if you see, let us consider the x-intercept. These are the axis lines, and the point where the plane touch that axis line will be the intercepts. Okay, so if you consider the x-intercept, this is the x-axis, and this is the line of the plane. Now we can see here one of the boundary line which is making up the plane is parallel to the x-axis. These both bases are parallel to each other. That is why this plane will never intersect x-axis, because this plane is parallel to the x-axis. Okay, so two parallel lines never intersect each other. That is why if we consider this plane 2, then this plane 2 will never intersect the x-axis, and since that plane never intersects the x-axis, what will be the x-intercept in that case? It will be infinity. So the x-intercept in our case for plane 2 will be infinity. Okay, now consider the y-intercept, and this is the origin, this is the positive y-axis, and it is lying in the opposite direction of the positive direction, so it will be negative y-axis. Okay, and it is lying in the negative y direction, and this will be the full length. Okay, and it is lying in the halfway direction. We can also see in the image that this is the full length one, but it is at the middle. We can see here that is it is lying just as halfway from the origin. Okay, along the y direction. So the y-intercept in that case will be -1/2, because it is in the negative direction. That is why. So y-intercept in that case will be -1/2. Okay, and the last intercept is the z-intercept, and for this we can see here also that this line, and this line, the axis line, and the this line and the axis line, both of them are parallel to each other, so they will never intersect. Also in that case, in plane 1 case, we can clearly see that all these main lines that defines the plane are making some angle with z, x and y axis. That is why their intercepts were non-infinity. Okay, but we can see here that these main lines that defines the boundaries of the plane 2 are either parallel to x-axis or z-axis. In plane 2, the main boundary lines that defines the plane 2 is these lines, and these lines are parallel to the axis that we have defined. So that is why in these cases we have infinity as the intercept, but it was non-infinity when these main lines are making some angle with the 3 axes. Okay, so ultimately they will intersect the axis at some point, but for the parallel lines making up the plane, they will never intersect. So these are the 3 intercepts that we got. Now the next step is to take the inverse of these intercepts, and the inverse of infinity is 0. Okay, whenever infinity is 0, so 0, and inverse of -1/2 is -2, and inverse of z-intercept is 0. Okay, infinity is inverse is 0. So we got 0, -2 and 0 as the final numbers for the Miller indices, and we'll write them in the rounded brackets. And first inverse of x-intercept, second is inverse of y-intercept. Since it is negative, we represent such numbers as 2 with a bar over it. Okay, these shows the negative number. Okay, and the last one is 0. So this is the Miller indices for these are the Miller indices for plane 2 right there. I hope it is clear to you. Now next one we'll solve the other problems. We are done with the first problem, and the method that we used here is also a part of that general method that I wanted to show you. So for the first preference, we'll use this method, okay, in which we'll analyze the plane in reference to the coordinate system. We'll see what are the most appropriate position of these coordinates, because we can see here that their position is quite obvious. That is why we could make idea of what would be the intercepts for these two planes. Sometimes the intercepts are not obvious, and we have to use some other method, which is what we call as a general method that will be used instead. Now let us see some of the other examples. And yeah, so here is another problem. We can see here there are the two planes whose Miller indices needs to be determined, and one of them is plane A and the other one is plane B. And we can see here that the plane A is in orange shade, dark orange shade, while the plane B is in mild orange shade. So we can clearly differentiate between the two planes. Now, first of all, if we consider the plane B, its Miller indices could be found using the method that I showed for the first example also. We can see here that the major lines which are defining the plane is these ones. Okay, these are the lines. The plane B is the simpler one, that is why I'm doing it first. For the plane A, we'll need the other method, that is why I'll do it next. So for plane B, if you consider the plane B is not passing through the origin. When the plane is passing through the origin, it will be like obvious. We can see in this example. Okay, here we can see both plane A and plane B are passing through the origin. Here is the origin. So the predefined origin is not suitable for our method, and we have to shift the origin in that case. But in other cases like these ones, the origin is not a part of the plane, so we can use the predefined coordinate system. So this is the predefined coordinate system, which has this line as a z-axis, this as x-axis, and this as y-axis. So axis lines are very important in determining the intercepts, because these are the lines whose intersection we want to find with the plane. So for the plane B, we can see here that this line, and these lines are defining the plane, and this line we can see here is parallel to the z-axis. okay, and it is not making any angle with the z-axis. That is why the intercept for the z-axis will be infinite. As we can see here, the plane is parallel to the z-axis, it is vertically parallel to the z-axis, and it will never touch the z-axis. That is why the z-intercept for the plane B will be infinite. Now if you consider the x-intercept and y-intercept, we can see here that this is the x-axis, and for x-intercept we have to see the x-axis and the plane's point where it touches that x-axis. So this is the line of x-axis and this is the plane, and it is touching it right here, okay, right there, it is touching it right there. So this is the x-intercept, and its position is mentioned already here, that it is halfway from the origin, right above there, okay. This is the position of that point from the origin. They have shown it, but we can also make an idea that this is half and this is also half, so this point is the halfway. Now sometimes you may get confused because the line is like it is a three-dimensional image, and some of the lines may appear curved or in the form of slope, so we could not make an idea whether this line is at the half point or not. Firstly, in most of the cases the intersection points are mentioned just like the problem I mentioned here. The 1/3 point is already mentioned above, you can see here, and first thing is this, and the second one thing is to make an idea of the best estimate of the position of the intersection point. One of the method I'll mention just later on in the video, just after telling you the y-intercept, I will mention that what kind of estimate or the method you can use to make the correct estimate. And for the y-axis, we can see here this is the total length, okay, this is the total length, and this point is the y-intercept, because at this point the plane is touching the y-axis. This is the y-axis and the plane is touching right here the y-axis, and this point is not the middle point. As we can see, this is the whole length, unit cell length along y-axis, and its half will be something like there, okay, but it is lying behind that middle point, and this is obviously they have shown it as 1/3, but we can also consider it as repeating this section 3 times, 1 time, 2 time and 3 time makes the whole dimension. So for if the dimension is half, if the point is half, then it means repeating it 2 times will make it 1, okay, or will complete the dimension of unit cell, and if it is 1/3, then it means repeating that part 3 times will complete the dimension of unit cells. So you can also confirm it like repeating it 3 times, 1, 2 and 3, it will complete the dimension of unit cell, which is from this to this point. So this is the 1/3 part, and this is the y-intercept, okay. So the x-intercept we found here is half, and the y-intercept is 1/3, and the z-intercept is infinite for the plane B. So for plane B, as I told, that x-intercept is half, y-intercept is 1/3, and z-intercept is infinite. And we'll take the reciprocal now, and the reciprocal of half is 2, reciprocal of 1/3 is 3, reciprocal of infinite is 0. So the Miller indices for the plane B in this case will be 2, 3, 0. So these were simple ones. Now let us consider the plane A now, okay. The plane A is this one, okay, and it is also not passing through the origin, so there is no problem with the predefined coordinate system. Hence this will be the origin, and this is the z-axis line, this is x-axis line, and this is y-axis line. Now let us see whether let us see where the plane A is intersecting these axes, okay. So this is the plane, and we can see here it is intersecting the x-axis line. This is the x-axis line, and it is intersecting it right there, okay. So this will be the x-intercept, and since it is lying at the edge of the unit cell, so the x-intercept will be simply 1, okay. So for plane A, the x-intercept is simply 1. Okay, because the plane is touching the axis at the end of the end point of the unit cell, at the corner of the unit cell. Now let us consider the y-intercept. So this is the y-axis, okay, and this is the y-axis, and the plane is clearly touching the y-axis at this point, and it is also at the edge of the unit cell. That is why the y-intercept is 1 also. So y-intercept is 1. All right, and lastly, for the z intercept, we can see here that this is the z-axis, okay, and clearly we can see here that it is not apparently within that single unit cell, is not intersecting the z-axis. Okay, it is lying right there, and this is not the line of z axis. The z axis is lying right there, and it is not touching it here, but somewhere if we extend the z axis in the negative direction, if we make some unit cell in the negative direction and extend that plane also in downward direction, then this plane will intersect the negative z axis. Okay, if we extend that plane, if I let me make it right there on the paper, and I will show you that it will somewhere touch the negative z axis when we will extend it in the backward direction. So here I am making the cube right there like that, and this is the z axis, this is the x axis, and this is the y axis. Okay, and this is our plane, okay, in single unit cell. And if we make other unit cells in downward direction, okay, and if we extend that plane, okay, it will somewhere not exactly at the edge of the another unit cell, but somewhere, that is not necessary that it will touch right there. This is a rough diagram, so it will, if we extend it in the downward direction, it will touch the negative z axis at some point, and we need to find out that point in order to determine the Miller indices for that plane. So know the two intercepts, the other two intercepts, which are x and y intercept, but we need to know the z intercept. For this we will use this method that is applicable to all kind of, like as I told earlier, to all kind of planes. And for this you need to use the point intercept form, which is also known as the equation of planes. Okay, and planes are actually the surfaces also. So yeah, and we have a over x plus b over y plus c over z equals to 1, where x, y and z are the intercepts. Okay, and a, b and c are any point lying on the plane, and this point needs to be determined very cleverly. If you use that equation cleverly, then you can determine all of three intercepts via using this single equation, where you don't have to make some guesses also. If you have any doubt on some intercepts, then you can use this method. So let me demonstrate it one by one, and make sure that you watch me solving all of the problems so that you can understand it well enough. That is why I'm making use of more and more examples. So we know that for this plane, for our given plane, the x and y intercepts are this: x is equals to 1 and y equals to 1. These are the intercepts. Okay, x, y and z are the intercepts. Here I denoted the intercepts with x, y and z. In some books it is represented by a, b and c as the intercepts, and x, y, z as the point, but I am representing these intercepts with x, y and z signs, and a, b, c are the any point on the plane. Now x and y intercepts are this, and we need to know the z intercept. And when we need to find out the z intercept, then we have to make sure that the point that we have chosen does not have the z coordinate as 0. Okay, because if c is 0, then the whole quantity will vanish and you will not be able to find out the z intercept. So the intercept you want to find, its point should be at least non-zero. Okay, any point that you are taking on that plane should not be 0 corresponding to that intercept. So for z intercept, we have to consider a point on the plane which do not have at least z coordinate 0. So let me again show you the picture, and we can see here that they are the three most prominent points on the plane, one of them is this, the other one is this, and the next and the last one is this. For this point the z coordinate is 0, and for this point the z coordinate is also 0, but for this point the z coordinate is non-zero. So this is the suitable point that we can take and put them into this equation in order to determine the z intercept, because as I told earlier, if we take these points, in these points the coordinates are such that the z coordinate is 0 right there, so we could not be able to determine the z intercept if the point we have chosen has the z coordinate 0. So we'll take this point, and for this point we can see here its coordinate is 1, 1 and 1. The three coordinates are 1, 1 and 1. A, B and C will be 1, because we can see here to reach that point from origin we have to move 1 unit x along x, 1 unit along x, 1 unit along y, and 1 unit along z axis, and then we will reach that point, and hence its coordinate with respect to that origin will be 1, 1 and 1. So the value of A, B and C that we'll insert here will be 1, 1 and 1, and the point that we have chosen to determine is this one point. Okay, so let us put these value right there, and all of them are 1 here. 1 over z equals 1. Now z needs to be determined, and z is the z intercept. Simply 1 over 1 is simply 1. 1 plus 1 is 2. 2 plus 1 over z equals 1, and 1 over z equals 2 gets right there, and it is minus 1. And if you take z in this direction and minus 1 in this, so we'll get z equals minus 1 simply. Or if you take reciprocal on both sides, then we'll get z equals to minus 1. So the z intercept is minus 1 here. Okay, so it actually touched the z axis at the edge of the another unit cell, okay, which is making minus 1, and this is point plus 1. If it is above the origin and at the corner of the unit cell, then it is 1, and if it is below the origin and it is lying at the end of the unit cell, then it will be minus 1. Okay, so it actually came out to be minus 1, but it is not necessary that by very. So yeah, these are the three intercepts. Now we'll take the inverse of these intercepts, which is again 1, 1 and minus 1. So the Miller indices for this plane is 1, 1, and for minus 1 we'll show the minus 1 sign by putting a bar over its sign. So this is these are the Miller indices for the plane A. Okay, now this was such an example in which we knew two of the intercepts and the other one needs to be determined. In the coming examples, we'll have a variation of problems in which maybe we do not know all of the three coordinates, or maybe we knew only one of the intercept and we need to determine the other two by using this method. So there are the other problems which are more tricky, so stay tuned to learn the whole method. And if you have any questions, you can ask me in comment section. So yeah, now next one is this one. Okay, they are the two planes. One of them is dark green and other one is plane B, which is in a light green color. Now the plane B is again a simpler one. Okay, the plane B is again a simpler one. We can see here it is not passing through the origin. It is like in this direction it is like that. I cannot show it. So it is like that tangentially. It is not passing through the origin. It is clear, and we can see here these are the axis lines, and this plane is touching the axis line clearly at these points. So we can determine its intercepts by seeing at the image. Okay, so this one does not require that point intercept form. Now for this, we can see here it is halfway above the origin, and they have also shown it in the picture. This is but also obvious one. If you repeat that length, then you will reach the end of the unit cell. So as I told earlier, if it is halfway above the origin, then it means repeating that length one more time will reach you at the end of the unit cell. So this is half for the z intercept. Okay, z intercept is half, while the x intercept, we can see here it is touching at the edge of the unit cell. This is the x-axis and the plane is touching it at the edge, and its x-intercept will be 1. And the y-intercept is also clear. It is touching it right there, and it is also halfway from the origin. So this y-intercept is 1 by 2 also. So we'll take the inverse, and after taking the inverse, we get 1, 2, and 2. And the Miller indices final. Miller indices are these ones for the plane B in this example. Now let us consider the plane A. Okay, and for which the plane A is clearly parallel to the z-axis, it is not clearly passing through the origin, so the predefined coordinate system is suitable. Now this is parallel to the z-axis as clearly shown. So these two lines are completely parallel to each other, these vertical lines. So the z-intercept is clearly infinite, and the other intercept which is clearly here is y-intercept. You can see here this is the y-axis, and it is touching the y-axis at that point. At the similar point the plane B was intersecting, so this is the half point again, and the y-intercept is again half, not again, I mean it is half. And we can see here the x-intercept needs to be determined, because now this is the x-axis line and the negative x-axis will extend in this direction, and it is clearly not touching the x-axis within that single unit cell. We have to extend the unit cell in backward direction, and we also have to extend the plane A in that direction such that it will touch the negative x-axis somewhere. Okay, and that point needs to be determined, because the intercepts are the point where the plane touches the axis line, and the axis lines are these lines, not these lines. These lines are not axis line. The axis lines is only fixed lines that we have predefined. So the positive axis line or the negative axis line. So x-intercept needs to be determined, and again the same rule will apply, that the point that we'll choose on the plane should be such that whose x coordinate is at least not 0. Okay, y and z intercepts are known, but x intercept needs to be determined, and the point that we'll take should be the point where the x coordinate is not 0. The x coordinate is 0 right there. It is 0 right there, but it is non-zero at this and this point. So we'll take the this one point, because this is the simpler one, where z is 0, and that doesn't matter because it doesn't require us to have the z part. We only need the x-intercept, and for which the point should have at least the x coordinate to be non-zero. So if you consider its coordinates, then from origin you have to move 1 unit along y-axis and half unit along positive x-axis, and you will reach that point on the plane. And hence the coordinates for this point on the plane are 1/2 along x-axis, 1 unit along y-axis, and 0 unit along z-axis. So these are the values for A, B and C. We will insert these values right there. First, 1/2 over x, 1 by y. I'll put the values for the intercepts at the end. This will cancel out. Okay, 0 by z is actually 0 again. So 1/2 over x plus 1 over y equals 1. We'll put the value of y right there, which is 1/2. The intercept for the y direction is 1/2. So we'll put right there, and we get 1 over 1/2 equals 1, and this one will go up and becomes 2. Okay, it is like 1 divided by 1/2, and if we change the sign from a division to multiplication, then it will just get inversed. So 2 is the answer of this fraction, and equals 1. Now 1/2 by x, this one goes there, and it is -1. Now we'll take the inverse on both sides. X over 1/2 equals -1, and x equals to 1/2 goes right there, and this is the x-intercept. Okay, so we had y-intercept 1/2, z-intercept half, and x-intercept came out to be -1/2. Now we need to take the inverse of these three intercepts, and the inverse of -1/2 is -2, inverse of 1/2 is 2, and the inverse of infinity is 0. So the Miller indices for the plane becomes this. Okay, these are the final Miller indices for the plane. All right, now let us see the last example, for which we have to shift the origin also. For both of the planes we have to shift the origin. As we can see here that plane A, this is in a dark blue shade, and it is passing through the predefined origin. This is the origin, and it is passing through the origin. And the plane B is also passing through the origin. So we need to shift the origin, and the new region that is suitable for both of them is this one, or even this one. So for simplicity, I'll take this one as the new region. So this one point is now the origin point, This is negative y-axis and this is positive y-axis. This is the x-axis and this line will be the z-axis. So I have to redraw it on a paper so that the axis lines are well defined and I can show you the method properly. So I'll find out the Miller indices for plane A first, and then we'll find out the Miller indices for the plane B. And here clearly we have to use the point intercept form in order to determine all of the Miller indices or some of them. So let us start. First I am drawing it right there. Okay. This was the predefined origin, but now I am taking that point as the new origin. Okay. Because the plane was passing through it and the axis lines are this one, and above the origin is z-axis. This is z-axis, z prime, this is minus y prime, this is y prime positive, and this is positive x-axis. Okay, let's say to differentiate it from the one that is mentioned right there, notations, to change the notations I just put prime over them, over their sample. So this is the new coordinate system that we will use as reference to determine the Miller indices for the plane. And the plane A is one of the point on plane A is right there, the other point is there, half, and the last point is there. So joining these 3 points will give us the plane A. This is the plane A. Okay, so this is the plane A as you can see here, and this is the point where I took the new origin, new coordinate. I defined the new coordinate system. So for plane A we can see here that this is the z-axis line. Okay, and the plane is touching the z-axis at this point. Now consider the new axis lines only, forget the predefined lines. Now these are not our reference lines. Okay, these are the reference lines with which the intersection points needs to be determined. So this is the point where the plane is touching the z-axis. Okay, so this is the z-intercept and it is clearly lying at the edge of the unit cell. So the z-intercept is clearly 1 for plane A. This is plane A as mentioned in the problem. And for y-intercept, we can see here this is the origin, this is a positive y-axis, and it is not clearly touching it at the positive y-axis direction. But if we see in the negative y direction, this is the negative y-axis line, it is touching right there at the edge of the unit cell in the negative direction. So this is the -1 point along y-axis, and this is the y-intercept as it is touching the y-axis line at this point. So this is the y-intercept, and x-intercept needs to be determined because we can see here that this is the x-axis line. Okay, and the negative x-axis line will be lying like in this direction, and it is not clearly touching it apparently in that single unit cell, but it will be touching at some other point which could be in positive x direction or negative x direction, but we need to determine it. So we'll use the point intercept form, and for this we'll use that formula in which we have intercepts in the denominator and any point on the numerator, as we call it as point intercept form, in which we have point in the numerator. These are the coordinates or points, while intercepts are in the denominator. Okay, 3D form. So we know the value for y and z, but for x intercept we want to determine x intercept, and we need to find out a suitable point on the plane for which at least x coordinate is not 0. Okay, the value of b and c doesn't matter, but the value of a should not be 0. So for this, if you consider this one point, this is clearly along the y-axis, and along axis line the other two coordinates will be 0 obviously. So these 2 points do not qualify because the x coordinate is 0 in them, but it is non-zero right there. So let us find out the coordinates for this point, and we'll use this point on the plane to determine the x intercept. And for this, if we move 1 unit along y-axis in negative direction, along -1 unit along y-axis, plus 1 unit along positive z direction, and 1/2 unit along x-axis, then we'll reach that point. So the coordinates of this point becomes 1/2 along x-axis, -1 along y-axis, and 1 along the z-axis. So these are the value of a, b, and c Okay, I hope you know how to determine the coordinates of a point. So we determine the coordinates of that point on the plane, and we'll put these values right there. And the y-intercept was -1 also, c was 1, and z is 1 also. So 1 by 2 over x, -1 cancel out and becomes 1, plus 1 equals 1. 1 by 2 over x plus this becomes 2, and if we take it in this side, so it becomes -1. Now we'll take inverse on both sides, so it becomes this, and 1 by 2 goes over there and it becomes -1 by 2. So the x-intercept that we got here is -1 by 2. So the x-intercept is -1 by 2 here. Okay, so the Miller indices are, let us take inverse of these three intercepts one by one. It was -1 by 2 for x-intercept, -1 for y-intercept, and 1 for z-intercept. Taking inverse, it becomes -2, -1, and 1, and 2 bar, 1 bar, 1 are the final Miller indices for these planes. Okay, now let us consider the last plane whose Miller indices I'll be finding in this video, and this plane is clearly the plane B. Okay, and I'm drawing it right there. I have redrawn the cube, and the other plane was like that, the 2 points over there, and joining these also points together, and this is the plane. Okay, it is lying flat right there, and this is the next plane B. Okay, as you can see here. Now these are the lines of the axis. Okay, now let us see where that plane is touching these lines. So for y-intercept it is easy to determine, that is why I'm writing it first, because we can determine it just by inspection and looking at the plane. So we can see here this is the origin, and this is a negative y direction, and the plane is touching the negative y direction at the edge of the plane. So this plane is touching the y-axis at this point, and this point is in negative direction. That is why we will take -1 as its intercept. So the y-intercept is known here. Okay, but for x-intercept, we can see here this is a positive x direction and this is a negative x direction, and it is not clearly touching it within that single unit cell with these axis lines of the x direction. So we need to determine it using the point intercept form. Also for the z-intercept, we can see here it is not touching the z-axis line. This is a positive z direction, and this is a negative z direction, and it is not touching clearly within that unit cell with these axis line. It will touch somewhere upward. If you extend it upward, then it will touch the positive z direction, the positive z axis somewhere above that unit cell, but we need to determine it. So in that case, we are going to use the point intercept form to determine two of the intercept, while we know only one of them, which is -1. So let us determine the x-intercept first, and because we are determining x-intercept, that is why the point that we should take should have at least x coordinate to be non-zero. Okay, and secondly, because we do not know the value of z-intercept, and the formula requires all of the intercept, so we cleverly choose a point where c should be 0 also, so that we do not need to put the value of z-intercept, because we don't know the value of z-intercept, and also the value of x-intercept needs to be determined. So there could not be two unknowns in a single equation. So to remove that difficulty, when we don't know two of the other intercepts or one of the other intercept, then their points, corresponding points, should be 0. Now since we don't know the value of the z-intercept, so the point that we are choosing on the plane should at least have x coordinate non-zero and z coordinate to be necessarily 0, because if we don't take it 0, then we'll have a problem, as we don't know the z-intercept. So let us take the first point, and the x coordinate should be non-zero while the z coordinate should be 0. Now these are the base points. Okay, and the base points are actually the points along which the z coordinate is 0. So we know one of this point and the other one is this point. At this point the x coordinate is 0, so we cannot take that point. We'll take that one point because the z coordinate is 0 right there. the x coordinate is non-zero, so both of the conditions are satisfied. So to reach that point from that origin, we have to move 1 unit in negative direction, -1 along y-axis and +1 unit along x-axis. So the coordinates of this points are 1 for x, -1 for y, and 0 for the z. So these are the a, b, c values that we'll insert in the point intercept form. So let me write the point intercept form, and let us first put the value of the points, and it is 1 for a, -1 for b, and 0 for c. So this value will vanish, and we'll simply left with this term. Okay, and we know the value of y-intercept, so x-intercept could be easily found. So y-intercept is -1, so we'll put the value -1 right there. And if we do it, then -1 over -1, this -1 and -1 gets cancelled out and it becomes +1, and 1 over x equals 1 -1, and which is 0. 1 over x is 0. It means if we take the inverse, then it will become x equals to infinity. Okay, as we can see here also that these lines were parallel to each other, but just to show that when we don't know two of the coordinates, I wanted to demonstrate it. That is why I didn't take the x-intercept directly as infinite. Okay, so just to demonstrate it, that when we don't know two of the intercept, then what kind of approach we'll use to find the two intercepts using the point intercept form. So just to demonstrate it, the x-intercept is infinite, and let us now see what will be the z-intercept. So for z-intercept, since we now know two of the points, two of the intercepts are known, like, and x-intercept is known now, which is infinite, and y-intercept is known also. So there is only one restriction, that the z coordinate should be non-zero. There is no condition on the other two values. They could be any values. The points could be any values. So we'll take this point because this is a simpler one. And to reach that point, we have to move 1 unit along z axis and -1/2 unit along along y direction. Okay. We can see here it is lying at the middle, and it is also demonstrated in the image. So 1 unit along z-axis and -1/2 unit along y-axis, and no movement along the x-axis. So the coordinates for this point is 0, -1/2, and 1. Okay, so let us use the point intercept form to determine the z-intercept now. So a, b, and c, let us put the value of these. So this is 0 over x, -1/2 by y, plus 1 over z equals 1. So this will cancel out, and we'll left with -1/2 by y plus 1 over z equals 1. Now the y-intercept, as we know, is -1. So -1 minus gets cancelled out, and we are left with this. Now 1/2 gets over there, and it is -1/2, and 1 minus 1/2 is 1/2. And if we take reciprocal on both sides, then we will get z-intercept as 2. Okay, so the x-intercept was infinity, y-intercept was -1, and z-intercept was in 2. So let us take the reciprocal, and after taking the reciprocal, we'll get 0 as corresponding to this, -1 again, and 1/2 here. Now a fraction appeared, and we have to remove the fraction. And to remove it, we'll multiply these three values with the LCM of the denominators, and the LCM of denominator is clearly 2. So we'll multiply each value with 2. These 2 and 2 cancel out, and this is 1, this is -2, and this is 0 again. So the Miller indices will become 0, 2 bar 1 for this plane B. Okay, you can use this point intercept form to determine all of the intercept. If you don't know for sure any of the intercept, if any of the intercept is not known, then you can even use that point intercept form by cleverly choosing a suitable point, such that if you want to determine the x-intercept only and y and z-intercept are not known, then choose a point on the plane for which b and c are 0. Okay, for which y and z coordinates are 0, then you will be able to determine the value of x easily, because a is non-zero. So you will determine x, and for the second point you at least have x-intercept known, so you can use any other point. Like I have clearly demonstrated the method, and I hope you understood what I'm trying to convey to you people. So I hope this video was helpful to you all, and if you want me to do other videos also in English as language of instruction, then you can comment down below. I will surely do that. And I'm also doing it for the other videos to define to find out the planar density for various planes for FCC, BCC and SC unit cells, and linear density problems, all of them. I'll be trying to upload a video in English as language of instruction, because I have already uploaded those videos, but those are in Urdu, Hindi. So I'll definitely do it for you if you want it, and I'll put the link of those videos in description box, the ones I did in English language. So I hope it helped you, and I'll be very thankful if you like it, share it and subscribe to my channel. Thank you so much.